Start.
Welcome everyone. Our project's titled is Deep Learning Based Techniques for Brain Tumor Classification in MRI Scans. We are three team members, Rishabh Jain, Ashish Rajpurohit, and Sam Ferguson. The brain tumors pose a severe health risk with potentially life-threatening consequences if not treated early. Challenges in manual interpretation are it is very time-consuming and subjective in nature. So we plan to automate brain tumor classification and MRI scans using deep learning, which will enable reduced diagnostic variability, faster and more reliable tumor identification, and increased accessibility to diagnostic expertise. Our problem statement includes automatically classifying brain tumors from MRI scans into four categories: glioma, meningioma, pituitary, and no tumor. So this multi-class classification problem is challenging due to subtle differences in tumor appearance, location, structure, and variations in MRI scan conditions. Our goal is to evaluate deep learning architectures to identify the most effective models for distinguishing tumor types while ensuring robustness to variations in MRI scans. Our dataset is compiled from multiple sources encompassing 7,023 images of MRI scans of the four tumor types. It integrates diverse tumor appearances and variations, ensuring a comprehensive representation for training deep learning models. The dataset is available on Kaggle as well. Our project uses 2D grayscale MRI scans as input for deep learning models stored in JPEG format and captured from various angles. To ensure consistency, images are resized and normalized before training. Data augmentation is applied to enhance model generalization as well. The models classify scans into four categories and outputting probability scores for each class, with the highest determining the diagnosis. These are the baseline performances for our three models that we chose: random forest, supervector machines, and convolutional neural network. Out of these three, random forest perform with 89% validation accuracy. The common attribute among these three performances is that each model performs detects confusion between glioma and meningioma classes. For our main methodologies, we chose ResNet 34, Connext, and combination of YOLO V11 and DenseNet, which we will discuss later.
So the first model we trained was the ResNet 34 architecture, which was introduced in the 2015 paper, Deep Residual Learning for Image Recognition. The main component of the ResNet architecture is the residual block, which is composed of two convolutional weight layers plus the identity mapping. While deep networks typically suffer from vanishing or exploding gradients due to long sequences of activation functions, the residual block is able to mitigate this drawback by providing identity mapping throughout all layers of the network. This is the architecture of the ResNet 34 model, and we trained it for 100 epochs using the Atom Optimizer with a learning rate of 10 to the negative 4. So as you can see, this model did much better than our baselines, achieving an accuracy of 99% on the validation set. Additionally, it no longer had an issue distinguishing the glioma class from the meningioma class, with a recall of at least 98% across all four classes. And this is the associated confusion matrix.
So the convex is a modern CNN architecture that was introduced in 2022 that combines traditional convolution approaches with design principles from vision transformers. The core innovation of convex is in the specialized building blocks, as shown on the left. It uses stepwise convolutions with large kernels to capture spatial patterns and followed by pointwise convolutions for channel mixing. This is the architecture that we chose for convex methodology, and the model was trained for 100 epochs with Atom Optimizer and the learning rate of 10 to the power minus 3. This is the model accuracy and loss plots. As we can see that the curve shows rapid improvements for the first 10 epochs, reaching about 90% validation accuracy and then gradually improving to 95%. Uh, this is the result for convex, which provided a great accuracy of around 94%. And we can also see from the F1 score that the issue with that the base models was having about glioma and meningioma was no longer present with an accuracy reaching of more than 87 to 95%. This is the confusion matrix associated with the convex architecture.
The third methodology that we pursued was a combination of YOLO V11 and DenseNet. Both networks are pioneers in image classification. However, this paper validates superior feature extraction capabilities of YOLO V11 run in synchronization with classification capabilities of DenseNet for a better overall image classification performance. The model that we are presenting here is a combination of YOLO V11 and DenseNet, and The combination strengthens the backbone of DenseNet, allowing the network to extract richer and deeper features without significantly increasing computational cost. In short, DenseNet balances speed and accuracy thanks to YOLO V11's powerful feature extraction for image classification in our dataset. The model accuracy, validation accuracy is 99.237%, which is very high, and there is no confusion between glioma and meningioma classes, which is similar to ResNet and the third methodology, which is Convex as well. This is the associated confusion matrix. Coming to the comparison of baseline models with the main methodologies, all the baseline models confused between glioma and meningioma classes while performing better in no tumor and pituitary classes. However, in our main methodologies, all three models do not confuse between glioma and meningioma classes and also consistently perform better in no tumor and pituitary classes. For prior work, all three of us have prior experience in machine learning and neural networks. This project was really fun. These are the references, and thank you.